All right. Hi, everyone. I'm Nicholas, and I'm joined here today with Alex.
Hi everyone.
We are two machine learning engineers in the machine learning team at Good Guardian. And today, yeah, we're super excited to talk to you about this topic that is absolutely capital when it comes to NHI lead management, which is prioritization. We'll show you the machine learning techniques that we developed to solve different challenges of prioritization and how we propose to combine them so that the security team will have a enhanced user experience and allow better security hygiene at scale. And before we get there, just want to take a step back and emphasize that the first step really when it comes to NHI leaks is detecting them, right? But when you're actually doing a too good job at detection, which is the case with our detection engine, you find the truth, and the truth is there are many leaks out there. Like really, secret scroll is a thing. I think everybody has to be convinced of this. We've had different presentations. I think one about Docker Hub was like even more telling about even leaks there. Leaks are everywhere. And when customers they take on the product, they expect maybe to see some incidents, some leaks, but they clearly don't expect that there are as many as they found out. And that's just the real truth of it. There are lots and lots of leaks, and we cannot just hand them out to security teams, right? If you just do secret detection without remediation, it's just noise. And the first step of remediation is prioritization. What is it? We want to show the security teams the most important incidents first. These are the little golden nuggets that you see in the picture. You want to pick them out and hand them to the security teams because, like any other team, security team, they have they have budget, they have time constraints, resource constraints, so they have to see what's most important first. And so that's something that you want to do with good prioritization. Show the most important incidents first, and on the other hand, you could think of there are secrets out there. There are real leaks, but they are here, let's say, on purpose for testing, or they have very low impact because they only access test resources. And those maybe you don't want to even show them at all to the security teams. You want to resolve them on the side so they can focus and allocate their budget better. Okay. So today that's what we're gonna show you how we do good prioritization. Before we get there, to emphasize even more that not all NHI leaks are equal in their threat levels. Alex is gonna show us just a few examples that make it even clearer.
Yeah, thank you, guys. Yeah, I think it's good to start with some examples. So here's the first one. So we can see here it's a developer who's doing a side project. He's coding a chatbot, and he's using an OpenAI key. And also, unfortunately, he has leaked it on GitHub, and it's publicly available. And here, what can happen? It's very simple. An attacker can use the key to do some to use the OpenAI models, and it will cost like maybe a few $1,000, but it's still manageable. I mean, few $1,000 at the company scale, it's still manageable. It's can be rotated easily, and it will not harm like publicly the company. So here we have an example of something manageable, like with not that high priority. But in other cases, it can be like really devastating for the company. It can have serious like reputational damages. It can have legal repercussions. So here we have three examples. So for example, you have the Schneider data leak with like hundreds of thousands user records that have been leaked. So devastating for the reputation and can also have like legal repercussion. You have the Cisco incidents. Like the attackers, thanks to leaked credentials, they gain access to hundreds of virtual machines. So you can imagine what an attacker can do with this type of access. It can be like really devastating for the company. And you have also the Uber case with like millions of customers impacted by a big leak. So here you can see like this just with simple publicly leaked credentials, like company can be like under serious, very serious threats. And so now to find these really like serious threats, we want to prioritize, but it can be a bit hard to prioritize because there is three main pain points. So you have the missing context, because it's hard to know, to understand what are these NHIs, what resource does they access to, how are they used to, like are they testing credentials, are they production credentials? You can also have too much information. Like, okay, you can find a lot of context around secret, but if you have too much information, you can be lost, and you need a simple way to show the instance and to understand it, like a simple scale to run them. And you have also a large number of situations. It's very difficult to have something like very general, which is working for every project, every team, etc. So like a lot of difficult situations. So maybe we first, so here the idea of the presentation is to focus on how we are using machine learning at GitHub to resolve all these issues. And the first one will be about the missing context, how we deal with this context, how we find more context at GitHub to help us prioritize the secrets.
Yeah, I mean, this example from Alex, they're like really, the examples that was showing was really critical. The context can tell a lot. Like, beforehand, you might not know that this leak, this NHI is actually going to be production related, and that the impact is going to be that. So that's what we want to do here. We want to gather the context that allows you to prioritize better beforehand, and find those really golden nuggets, these critical leaks first. And so, I just want to show you one last time maybe why context matters. Might be obvious, but just for the sake of it, here you have two incidents. The first one is, let's say, found by a GitLab token, and then you see the code patch here. It says connect to GitLab. You have a GitLab URL. When you see it, you get a sense of what it is, and if this is leaked, if someone accesses it, what he can do with it. On the other hand, you have this other incidents, the generic key detector that is most likely, given the look of the patch, it has to be a secret of some sort, but we don't know anything more about it. We don't know what even resources could be concerned with this. It could be extremely dramatic, or it could be absolutely unimportant, like going to see the weather or something. So without context, here you cannot say much. And I think you would say that the first one, the GitLab one, is way easier to prioritize, either critical or not critical at all. I don't know, but at least you have information to make that decision. All right. And so context can come from various sources. It first comes from non-machine learning sources. I want to emphasize that you don't need to do machine learning for everything. So here, for example, is a context that we already use at GitGuardian to do prioritization. And it's the places in which the secrets can appear. And you have an OpenAI key, let's say, that is vaulted in one of your internal vaults, right? What if you also find out that the same key happens to be hard-coded on a private repo on GitHub? Well, that's already a sign that this is a bit problematic, right? Because it's at the same time in a secure vault and in plain text in the code. That's a problem. Maybe you start to think it's a bit critical. What if the GitHub repo is now public? That's even worse, because you have at the same time a credential that was in an internal vault, and that's now on public GitHub. So the place in which those leaks occur is the first signal, not machine learning related, that can tell you a lot. Second example here is in the secret itself, sometimes you have information about where it comes from, what you can do with it. That's the case for JWT tokens. They always have, for example, an expiration date that you can see here. It tells you, for example, well, if the token is already expired, maybe it's not critical at all, because if someone accesses it, what can the person do with it, right? But also can tell you things like who issued the token, bitcarry.com, or other metadata like the role here, administrator. When you read this, you can start to feel a bit more concerned that if the role was something of lesser importance. All right. Last example of a context that is not ML related is, generally speaking, the scopes, the permission that a secret can give access to. And here it's an OpenAI key, and you have 3 different levels of permissions. The first level of permission is just, it just gives you access to the API that lists the available models on OpenAI. Well, I mean, if someone steals your key, what can they do with it? They can just list the models available, maybe not even internal models, maybe just public models. I mean, that is not really threatening at all. But if you go to the next level, here it would, for example, allow you to call the chat completions route. And this is the route where you can make inference with OpenAI models. Here, it's a bit more important, because if an attacker can access this, well, they can spend money with your key. That's the example that Alexandre was showing before with the OpenAI key. Maybe they spend thousands of dollars with it, which is non-negligible. They can maybe also throttle a bit the quotas, so that's not something to take too lightly. But again, it's not as worse as the last level, where the key would give you access to, let's say, a files route, where you're allowed to download files that were uploaded to OpenAI. And sometimes people, they upload user data to OpenAI to make inference or retrain a model or whatnot. And so if an attacker gets access to this, they can now get access to user data. And now we're talking about much bigger repercussions. So same key, different levels of permissions, vastly different impacts. Okay, so those are all examples where we don't use machine learning to do any of this. But we often need to go beyond the signals and get more context to do good prioritization. And that's what Alex is going to show us, what we did for this, how we did machine learning to enrich the context of the secrets.
Yes, exactly. So without machine learning, we already have access to really valuable data context for the secrets. But at the Guardian, we wanted to go beyond, to gain access, to create a knowledge, a capacity to extract data information from the secrets that go really beyond at the maximum level as possible. So as you may know, at Guardian, we have like a generic detection engine, which is able to coverage a lot of secrets, to find any secrets which are findable. But these generic secrets, we don't have at the beginning a lot of information on them. That's why we created an internal model, which is called the generic secret enricher, which is able to identify which provider is corresponding to any generic secrets. So here we have an example. So we have an API key, which is found by Token Scanner, our detection engine. And on the context, as a human, you can really easily find out that this is a Cloudflare API key, because you have the mention of Cloudflare as an API, and you can see that the API is used to gain access to this Cloudflare API. The first way to automatize these findings would be the first idea would be to create a regulatory expression, as we do for detection. But we tried it, and I would say good luck to those who want to do it, because it's really tough to, on the one hand, have a really good record to find all these examples, and on the other hand, you need to have a good precision, because you don't want to have false positives. So it's really difficult with regular expression and classic techniques. And that's why we decided to train a model which is able to understand the context the same way as we are, to say, okay, here I'm able to say it's a Cloudflare API, and the API key is related to this API, so it's a Cloudflare related API key. And he can also give like a confidence, and it's really helpful for the prioritization. We also have other models, so we are able to say to have a model which is able to say, okay, this is testing related secrets. So he tried to find as much clues as possible. Like you have a test case in the comment of the class. This testing model which you mentioned. You have many clues, which is helping the model to say, okay, based on the context, I can say this secret is very probably related to a test environment. And the model is able to give a confidence score like from 0 to 100, and it's really helpful then for the prioritization. And finally, we also have the false positive remover, which is our model is able to identify like the mistakes made by detection. So in the example here, we can see that we have a secret detected in the requirement.txt, but we can see that in fact it's like a package version, which unfortunately the package has the word secrets in its name, and the version is like weird random. It could be like an API key or something. It looks like an API key, but in this case it's not. But actually to make sure we have a really good coverage, a really good recall for our secret detection engine, we have to detect this kind of like border, like they are at the limits. In this case, not, but it could have been a real secret. And then we use an hybrid detection with this machine learning model, which is able then to remove like more than 80% of the mistakes made by the regular expressions. And we are able to remove almost zero real secrets and remove almost all the mistakes. If you're interested, we have a blog article. I encourage you to read it. It's really interesting. Okay, so now we have seen that we are able to extract a lot of really interesting context to better understand what are these secrets. But we have so many like information that it would be overwhelming for the user. So we need to think about a way to present it to this end user. And I can.
Yeah, I guess I showed some, and then Alex showed more. You have, we enrich the context a lot with or without machine learning, and then we get a lot of it. We really don't want to show it to you like this. When we make the slide with Alex, it was like the reaction we're hoping to get is, what is this? It looks ugly, basically. It's just like a dashboard, and you can imagine having like all those different like signals. All this secret is publicly exposed, but it's also 70% likely to be a test. But it's also, in a sense, DeFi pattern here. And well, it's, I don't know, maybe it's a bit old, I don't know. So you don't want to have this, because with that information, you cannot do anything. It's like, it's noisy. How do you combine them? Is it critical? Is it not? It's, we need something better. We need something easier and to understand, more efficient. We want something like that. Severity, critical. This is top 10% of all your incidents. And actually is critical because XYZ, an explanation of why we had this decision, all right? That's what we want to get in the product to make it easier for security teams. We had an approach at the Guardian to first solve this issue, which was called severity rules. It's basically taking all those features, those input dimensions we just mentioned. So is it data storage? Is it a valid secret? Is it deleted now? Etc., etc. And make combinations of them. And if it's both data storage and valid, then it's critical. If it's invalid and deleted, then it's a low severity, etc., etc. And you could imagine having more and more rules to cover everything. The problem is, if you do this approach, well, first it becomes hard to maintain. So Guardian provides some severity rules, customer can define some, but then as soon as you have hundreds of them, it's very hard to maintain, right? Understand what happens, debug, fix, etc., etc. So that's the first thing. The second thing is this, by definition, will only give you the severity of incidents that match one of the, I don't know, 100 rules. If an incident doesn't match any of the rules, then you just don't know what the severity is. And that may be very problematic if a lot of incidents end up having unknown severity, because some of them might be extremely critical, right? And so to resolve those pain points, we migrated from this to a machine learning model, different type of machine learning model that Alex will present to solve those pain points.
Yes, really, the idea was to go from like a good entry point based on the rules to a machine learning model which is able to both increase the quality of the prediction of like the severity of secrets and increase the coverage to 100%, because we want to be able to compare all the secrets, and yeah, that's the ultimate goal. So to train this machine learning model and to predict the severity score based on this model, we have used all the context, all the features we presented you before, like a few slides before, which can be based on deterministic data that we can extract on the secrets, and also our ML-powered features based on our internal models. And so we provide these input features to the algorithm on the one side, and on the other side, we have been able to annotate large data sets of data of secrets with their actual severity. Like it could be, okay, this one is critical, this one is a medium severity, this one is low, this one is green data searching, it's very low. And then by giving this input and output to the algorithm, the model is able to learn what is severity of the secrets, and what are the features that are important to determine the severity of the secrets. And then he's able to compute a score for every single secret. And so we can compare the secrets based on the score. So to train the model, so we took two approaches. So really, it's really important to precise that all our models are internal, so we don't send any data to third parties, and we don't send any sensitive data to the model. We only use like the context data, not this like the secret itself or etc. Only like context data to create this score. So the first step was to understand what is the severity for like an end user. What is important for user, what are like critical secrets, what are not, based on how they play themselves with the severity in the platform. So it was really insightful. We learned a lot of things, but it also has a lot of human errors, and we have specific behavior from one customer to another that can be different. So it's really difficult to generalize. So we decided to take a second approach to train the final models, which is like creating an expert knowledge. And with this knowledge, we are able to define precise guidelines to annotate thousands of data, and then to train and evaluate our models based on this data. So we obtain like really good results. On one hand, we have the top incidents, like the critical secrets, that are 3 times more critical than with the current rules. So it's like when you will see a critical incident, you know that it's an important secret. So it's important. You can gain a lot of time, and we're also able to remove the noise. So like the top 10s on the bottom, the less important secrets can be like ignored without losing any like high important secrets. And you also have like the full coverage, because the model is able to compute a score on any secrets. So that's great to have like a really good severity score, high performance, but we think it's not enough. We think we can go even beyond for you. And the idea is, okay, we can say to you, this one is critical, this was not. But one thing I think also very important is to explain why. Why is it critical? Why is it not? And I think
Yeah, I mean, like Alex said, it's like the score is the first step, but if you don't understand the score, it's not enough. And you often hear that machine learning it makes decision, and you don't really know why it did what it did. Actually, this model that Alex presented, it was designed to be explainable. It's those models that you can exactly say, if it did this, it's because of X, Y, Z. And that's something that you want for explainability. So you can say, not only this incident is critical and it's, I don't know, top 10% or it has this score, but actually give a human, readable, and understandable explanation of why this incident is critical in this case. And so that's the small example that you have here in the picture. For example, it's critical because it gives access to a Salesforce authentication, which is usually very sensitive. And also the I don't know the testing probability, the probability that this is actually touching tests resources is very low. So it's probably production related, et cetera, et cetera. And so not only do we want to give you text that explains it, we want to give you enriched text that when you hover over one of those boxes, it's going to tell you, okay, it's very unlikely to be tested. Here's why, and show you actual facts or elements in the code or in the finance or whatever that explains to you why it's not test related, so that you can fact check yourself, or default branch, if you want to go to that branch and see, you can click on it and it will lead you there. And so this enriched text is really something that's going to allow the audits of the decisions of the model. And here I put a little example of how it works from the model perspective. It's really what Alex explained before, but imagine that the score is 5 at the beginning. Well, because the false positive remover that was presented gave it a very high likelihood to be a mistake, it lowers the score by, I don't know, 1.98. And because no team is assigned, it lowers it even more. But on the other hand, because the detector category was data storage, which is known to be sensitive, then it bumps up the score by 3 points. And when you do the whole addition, you end up with that score. And so that's very important because, well, first it allows to understand, what happens behind the model scores and everything. It also allows to, verify, is it really doing what I expect it to do? For me, if having data storage is not that important, maybe I want to give feedback so that the next version of the model is not going to weigh it as importantly for me as it did here. And so those are really important to provide to the security teams on top of just the score, so that they can audit and improve the model over time for even better experience and prioritization. And so yeah, I guess just the things we want to leave you with in these presentations. The first one is just repeating detection. That's the first step, but detection without remediation is just noise. You really want remediation, and remediation requires prioritization. Prioritization requires three things that we presented with Alex: the richer context, whether it comes from machine learning or not. You really want to enrich the context to understand what's happening and prioritize accordingly. That's the first step. The second thing is a good algorithm, machine learning based in our case, that can ingest this context and give to the end user something very simple, very efficient, that allows to compare between two incidents, a rank, a score, whatever. The last point is an explainability module that will go beyond the score and give you an explanation on the model decisions and how it's arrived at that score. And so those three things really are what makes a good prioritization. And at Good Guardian, we developed machine learning models for all these different use cases. There are very different models actually that are tailored for those specific applications. They're all internal proprietary models. And yeah, I guess it's important to know that you do machine learning for a very specific use case, and because that's what works best. So yeah, thanks for listening, and we'd be happy to follow up later on the presentation.
Thanks.
Thanks. Bye.
Bye.